Okay, so let's now talk of operations on set. Operations on set. So under this we are going to look at concepts like intersection of set, union of set, disjoint set, and complement of set. Alright, so these are the four concepts we are going to look at under operations on set. So let's begin with intersection of set. Now, when we talk of intersection of set, all we are saying is that what are the members that are common to two or more sets given. So with intersection of sets, assuming we have two sets, okay, assuming we have two sets, our objective is to determine members that can be found in one set at the same time can be found in the other set. So we are looking at the common members, okay, the common members, what they have in common. So set A, if set A is equal to 1, 3, 5, 7, 9, 11, and set B is equal to 2, 3, 5, 8, and 9. Now if I ask you to find A intersection B, by the way, this is the notation of the intersection. So it looks like an N, right? So this is it looks like an N. So if I ask you to find A intersection B, all I'm asking you to do is compare set A to set B and then identify the members that are in set A at the same time in set B. So clearly you can see that 3 is in set A, 3 is in set B, so 3 becomes part of A intersection B. 5 is in set A, 5 is in set B, so 5 becomes part of A intersection B. 9 is in set A, 9 is also in set B, so 9 becomes part, right? So that is all that we mean by intersection, the common members, the common members. So let's look at how we represent intersection of sets on a Venn diagram. Alright, so the two circles here represent the two sets. Right, so that is how we denote, or that is how we represent sets on a Venn diagram. We represent sets with circles, usually with circles, so it can be any shape, okay, but then the most common one is the circle. So the two circles here represent the two sets. Now because they have some members in common, what we do, we are going to cross the two circles, right? We are going to cross the two circles, and the point where the two circles intersect or meet, right? So the point where the two circles cross is where we put our intersection, right? So the shaded region here is where we put our intersection. So if we are to represent this on a Venn diagram, you are going to have the circle for A, circle for B, and then you are going to put the members that are common, that is 3, 5, 9, in the middle here, in the middle section here. Alright, so it means when you pick 3, 5, 9, you can find it in set A, and you can find 3, 5, 9 in set B as well. Right, so that is how we represent intersection of sets on the Venn diagram. Okay, so let's move on to the next operation of sets, that is the union of sets. Right, so union of sets. So union of sets simply means that you combining the elements of two or more sets given. Right, so union, you are merging the two sets into one. Right, so all you have to do is that you are going to compare one set to the other set, and then you are going to just put everything together as one. Right, so you are going to merge them. Right, so in listing the union of sets, we do not repeat the common members. Right, the reason is that if, for instance, so if you have set C to be equal to 5, 10, and 15, set D to be equal to 3, 5, 7, 12, and 15. Now if I ask you to find C union D, you are not going to repeat the common members. Right, so 5 is here, 5 is here, so you are not going to write 5, 5. 15 is here, 15 is here. So in listing the members of C union D, you are not going to write 15 and 15. Since they are the same, you're just going to pick one of them. Alright, and then with union of set, what you have to do is that you have to list the members in order. Right, in order. So assuming they are numbers, you have to list the numbers in order. Right, so you start with the least and then you end with the greatest. So you're going to start with 3, and then 5, and then 7, and then we come to 10, we come to 12, and then 15. Right, so that is union of set. That is union of set. So let's look at how we represent union of set on the Venn diagram. So because we are combining the members of the two sets together, right, it means that the shaded region here, represents the union of set. So everything within the two circles, come together to form the union of the set. Right, so everything here plus the intersection plus everything here, right, will give us the union of set. So if we are to represent C union D on a Venn diagram, we are going to have the circle for C and the circle for D. Right, now because they have common members, we are going to put the intersection in the middle here. Right, so the common members, that is C intersection D, is 5 and 15. So we're going to place 5 and 15 in the middle here. Then we are going to place the members of C only, right, C only here, that is 10, and then D only here, 3, 7, and 12. Alright, so if I ask you to tell me the members of set C, just picture or just look at the circle of C. So it is simply 5, 10, and 15. As you can see here, 5, 10, 15. If I tell you to list the members of set D, it is going to be 3, 5, 7, 12, and 15. So as you can see in the circle of D. Alright, but then the union encapsulates everything in the two circles. Right, so that is union of set. Okay, let's move on. Okay, let's now look at disjoint set. Disjoint set. So what are disjoint sets? So these are sets which do not have any common member. So they have nothing in common. Right, they have absolutely nothing in common. Right, so if we have set X to be equal to 1, 3, and 5, and then set Y to be equal to 2, 4, and 6. Now why do we say set X and Y are disjoint set? They are because there is no member in set X that can be found in set Y. Alright, so it means that X intersection Y is a null set. Right, so for any or for every disjoint set, or for two disjoint sets, we say X intersection Y is a null set. Right, so the intersection of the two sets is what is a null set. Right, so because they don't have anything in common, we don't cross the two circles. Right, so you have set X here separate from set Y, so you don't cross it. Right, so the members of set X is 1, 3, 5. The members of set Y 2, 4, 6. Alright, so whenever you see two sets apart, right, it means that they are disjoint, meaning that there is nothing they have in common. Okay, let's move on to complement of set. Complement of set. Now we make use of the term complement of set when we are comparing a subset to a universal set. We make use of the complement of set when we are comparing a subset to a universal set, and our aim is to identify all those members that can be found in the subset. Alright, all those members that can be found, all those members that can be found in the universal set but cannot be found in the subset. So let me repeat. Our aim is to identify all the members that can be found in a universal set but cannot be found in the subset. So let's take a practical example here. So our universal set is equal to 1 2 3 4 5 6 7 8 9 10. So from 1 to 10, that is our universal set. Our set A is equal to 2 4 6 8 10. So if I ask you to find a complement, by the way, the complement sign looks like an apostrophe. Okay, so there is it, like an apostrophe. So a complement, so the complement sign is denoted by an apostrophe. All right, so a complement is simply all those members within the universal set, that is from 1 to 10, that cannot be found in set A. So we are going to have our a complement to be equal to 1 3 5 7 and 9. Now 1 is not in set A, but then it is in the universal set. 3 is not in set A, but it's in the universal set. 5 is not in set A, but in the universal set. 7 is not in set A, but in the universal set. And 9 is also not in set A, but is within the universal set. So that is what we mean by the complement of set. Members of the universal set that cannot be found in the subset. Right? So if you have to graph it on a Venn diagram, now because complement means it is part of the universal set but it is not part of the subset, what you are going to do is that you are going to write the complement outside the circle of that set. Right? So the complement occurs outside the circle of that set, but then it is within the what? It is within the universal set. I believe you get me. So this rectangle here represents the universal set, but then within the universal set we have set A to be 2 4 6 8 10. But then there are other members in the universal set that are not in the set of A, so we put all those members outside the circle of A. Right? So the shaded region, the region outside the circle, is where we insert all our complements. I believe you get it. Okay, so let's move on. Alright, so let's now talk about the properties of operations on sets. The properties of operations on sets. So under this we are going to look at the commutative property, the associative property, and the distributive property. So let's start with the commutative property. Now when we talk of commutative simply means that the order does not matter, right? The positioning or the arrangement is not a factor. So irrespective of how you list the items, we are not interested in the order of it. If you have to cast your mind back to, I think, primary school, or let's say JHS, you would recall that your teachers usually tell you that addition and multiplication are commutative, right? So why do they say that addition and multiplication are commutative? The reason is that, for instance, if I have 5 plus 7, now you would attest to the fact that 5 plus 7, it is the same as 7 plus 5. Both of them will give me the same answer as what? As 12. So though here 5 plus 7, so the 5 came first here and then the 7 came second, but even if I am to interchange the position of 5 and 7 and I'm to bring the 7 first and the 5 second, it doesn't make any difference. It will still give me the same answer as 12. So addition is commutative, right? The same applies to multiplication. 3 times 4 is the same as 4 times 3. Both of them will give me an answer of 12. So even though I have interchanged the positions of 3 and 4, it doesn't make any difference to the results, right? And that is what we mean by the commutative property. So under basic arithmetic, addition and multiplication are commutative. Now under set, intersection and union of set are commutative, meaning that if I have A union B, it is the same as B union A. So although I have interchanged the positions of A and B, it doesn't make any difference, right? The same applies to intersection. So A intersection B is the same as B intersection A. Though I have interchanged the positions of A and B, it still doesn't make any difference. I'll end up getting the same members of the set. Alright, so that is the general overview of commutative property. Right. Okay, let's move on to the next property. Okay, so we have the associative property. Now, to help us understand this property, let's take a practical example, right, so that I will use it to explain it to you. So, assuming I give you set P to be equal to 4, 5, 6, and 7, and then set Q to be equal to 1, 3, 5, 7, and then set R to be equal to 2, 3, 5, and 9. Now, if I ask you to find I, P union Q in one bracket, and then union R, and then II, P union into bracket Q union R. So let's solve these two questions. Okay, let's solve these two questions and make an observation. So let's look at the first one. So I'm to find P union Q into bracket union R. So let's first find the bracket. Okay, so let's first find the members in the bracket. So what is P union Q? So we are just going to compare set P to set Q, and then we are going to merge them. We are going to put them together as one, right? So when we do that, we are going to have our P union Q to be equal to 1, 3, 4, 5, 6, and then 7. So that is P union Q. So we just combine set P to set Q, right? We combine set P with set Q. Then let's also combine P union Q with set R. So this means that we have to merge P union Q with what? With set R. And when we do that, we are going to have 1, 2, 3, 4, 5, 6, 7, and then 9. Right? So we just added set R to P union Q, and that gives us P union Q in one bracket union R, right? So that is for the first one. Let's look at the second question. P union into bracket Q union R. So here too, let's find the bracket first. Okay, let's find the bracket first. So let's find Q union R. So Q union R means that combine the elements of Q and R. So when we do that, we are going to have Q union R to be equal to 1, 2, 3, 5, 7, and then 9, right? And then we also compare Q union R with set P, and then we also merge the two sets, right? So we are going to find P union Q union R, right? So we are just going to add set P to this set, right? So when we do that, we are going to have 1, 2, 3, 4, 5, 6, 7, and 9. Now, what is the observation you are making here? You realize that I is equal to II, meaning that P union Q in one bracket union R is equal to P union into bracket Q union R. Now, this is what we mean by the associative property. So the associative property basically tells us that irrespective of how we combine any two sets, right, irrespective of how we combine any two sets, we are going to arrive at the same answer. We are going to arrive at the same result, right? So P intersection into bracket Q union R is the same as P intersection Q into bracket and then intersection R. Similarly, P union into bracket Q union R is equal to P union Q in brackets and then union R. Right, so this is an illustration of the associative property. Alright, okay, let's move on. Okay, let's now talk about the distributive property. Alright, so the distributive property. So here too, let me give you a practical illustration of how the distributive property functions. Okay, you would recall from your knowledge on algebraic expression that assuming you have an expression like x into bracket y plus z. Now, if you are told to expand this expression, you are going to arrive at x, y plus xz. That is x times y plus x times z. Now, so here we say that x has been distributed over y and z. And that is where we get the word distributive from. Right? So the distributive property simply tells us that assuming you have x, right, and then into bracket y plus z. Now let's look at this particular example. How did we get xy plus xz? Now we paired the x with the y and then we paired the x with the z. What did we use to pair the x with the y? We used multiplication. So xy is x times y, xz is x times z. Now bear in mind that this expression x into bracket y plus z, it is the same as x times, right? So the operation separating the x from the bracket is what? Is a multiplication sign. And that is the same operation that is used to pair the x with the two elements in the bracket. So we have x times y and x times z, and then the operation that was separating the two members in the bracket is what separated the two pairs, right? So we had xy plus xz. Now this is what we mean by the distributive property, right? So under basic algebraic expression, we say that x has been distributed over y and z. Now under sets, we say that if you have an expression as A union into bracket B intersection C. Now this is the same as A union B intersection A union C. Now let's look at the correlation between this and this. Right, let's try to understand this from the standpoint of algebraic expression. You see, with the algebraic expression, the operation that was separating the x from the bracket was multiplication, and that was the same operation that we used to pair the x with the two elements in the bracket. So we used the multiplication to pair x with y, and we had x times y, which is xy. We also used the same multiplication to pair the x with the z, and we had x times z, which is xz. And then the operation that was separating the element in the bracket was what was used to separate the two pairs, right? So we have xy plus xz. Here too, but we are going to apply the same concept. So we have A union into bracket B intersection C, right? So the A is outside and then B and T are in the bracket. So in distributing A over B and T, we are going to use the operation that is separating the A from the bracket to pair the two elements in the set with set A. So we are going to arrive at A union B and then A union C, and then the operation that was separating the element in the set or element in the bracket B and T, okay, it is what is going to use to separate the two pairs. So we are going to distribute A over B and C using the union sign here, right? So you're going to have A union B in one bracket and then A union C in another bracket. Then we are going to use the operation that separates the B and the C to separate the two pairs. Just as with the algebraic expression, the operation that was separating the X and the bracket was the multiplication, and that was the same operation we used to pair the X with the Y and the Z, right? So here we had X times Y and then X times Z, and then you realize that the operation that separated the Y and the Z was what was used to separate the two pairs. So we had XY plus XZ. Here too, the operation separating the A from the bracket is the union set, and that is the same operation we are going to use to pair the A with the element in the set. Sorry, the element in the bracket. So you're going to have A union B and then A union C. Then we use the intersection that was separating the B and C in the bracket to separate the two pairs. Alright, so that is what the distributive property talks about, right? So if you also have A intersection B union C, you are going to use the intersection to pair the A with the members in the set, in the bracket, right? So you're going to have A intersection B and then A intersection C. Then the operation that separated the two elements in the bracket is what will be used to separate the two pairs. So you're going to have A intersection B union A intersection C, right? So let's look at a typical example. So if set A is equal to 1, 2, 3 and 4, and then set B is equal to 2, 4, 6 and 8, and set C is equal to 1, 3, 5 and 7, and I ask you to find A intersection into brackets B union C, and then A intersection B in one bracket union A intersection C in another bracket. So let's solve the first one. So we have to first find the brackets, right? Always find the brackets first. Always find the brackets first. So our B union C will give us 1, 2, 3, 4, 5, 6, 7 and then 8. And then we compare B union C with set A to find the intersection, right? So the intersection will be 1, 2, 3 and 4. So that is for A intersection B union C. So let's move on to the second question. We have to find A intersection B in one bracket union A intersection C. So we are going to find the two brackets first, right? Then we find the union between the two. So our A intersection B will give us 2 and 4, because when you compare A to B, the only common members are 2 and 4, right? A intersection C is 1 and 3. So as you can see, 1 is here, 1 is here, 3 is here, 3 is here. So it is 1 and 3. So we are just going to find the union, meaning you are going to combine this set to this set, right? So A intersection B union A intersection C is equal to 1, 2, 3, 4. As simple as that. Now, what is the observation you are making here? You realize that I give us the same solution as I, meaning that A intersection B union C is equal to A intersection B in one bracket union A intersection C. Alright, so that is the distributive property. I believe it is well explained.